introduction and the invitation to the talk. It's my great pleasure to be here. So I'm a postdoc from Cambridge at DAMT, where I'm working with Enrico Payer on primordial cosmology. And today I would like to present some work that we call the open effective field theory of inflation. So the goal of this work is to extend the set of effective field theory techniques we have at our disposal to include effects that are local dissipation and noise. And so throughout this presentation, I will explain why we wanted to do this extension. I will start with some general motivation, then explain how we construct this sort of open effective field theories that include dissipation and noise. And finally, I will finish with some phenomenological aspects we can expect from this theory when applied to the context of primordial cosmology. So do not hesitate to stop me during the talk, either if there is something that is unclear, because I don't know the background of everyone in the audience. And also if there are any problem with the Zoom connection, do not hesitate to ask me and I'll repeat. So let's start with some general motivation that led us to this work. The starting point of this story is the so-called in-informalism, which is the formalism we use as cosmologists to compute expectation value of observables. And these expectation values of observables are important because they are the objects that we later on compare to the data we obtain either from the cosmic microwave background or the large-scale structure of the universe. So they are really the objects we want to compare to the data. And the way they are computed, these observables are slightly different from what we do in particle physics. It's much closer to what you might be familiar from your undergrad courses in quantum mechanics, because the idea is that you specify some quantum mechanical operator and you specified a specific theory that is given by a unitary operator, which is an object that tells you how a quantum state evolved from its initial state to its final state. For instance, we initially start at the beginning of inflation with a so-called Bunch-Davies vacuum, which is a vacuum state. And we end up at the end of inflation through to another state, which is in general much more complicated. And this object will tell you the dynamical evolution from initial time to final time. It has a path integral representation. If you express it in the field basis, you can express it in terms of a path integral, and you can see that the field content of your theory appears there through your action. And then if you want to compute the expectation value of some observable, you put a bra on the left, a ket on the right, and that's how you compute this expectation value. If you expand in the field basis, you put some representation of the identity, and you can see that you have two evolution operators that appear, one on the left, one on the right, that correspond to the bra and your ket you inserted. And this is why when you represent this in terms of a path integral, you have two insertion of the action, one with a positive sign and one with a negative sign. That means that your path integral will contain two branches, one that goes forward in time and one that goes backward in time. And this is why this formalism is called the in-informalism, because you only have to specify the initial state, but you do not tell what is the state at the end of, for instance, inflation or the period of interest for you. This formalism is often used in the context of non-equilibrium QFT because it's useful for two things. It allows to study the transient dynamics when you finish at a finite time, instead of what you usually do when you do particle physics, where you both specify the initial state and the out state. So that's the first interest of this formalism. And the second interest is that it's useful when you don't know all the degrees of freedom of your theory. So this is what we call an open quantum system. For instance, let's imagine that the degrees of freedom I really observe when I look at the sky are represented by a variable that I denoted zeta, that I call the system. And this system interacts with a hidden sector that I don't have access experimentally. That is, if I measure things on the sky, I won't directly see this degree of freedom. I will call this other degree of freedom the environment. And since we don't observe directly the environment, the goal will be to integrate out so that we want to write down an EFT for the system only, that is focusing on the degrees of freedom we really observe. And when you do this task in the Schwinger-Keldysh contour, that is it in path integral, the imprint of the environment is captured through a complicated object that is called the influence functional. This influence functional, when you compute expectation value, it appears on this side here. And so its effect is threefold. It can change the action that propagates along each branch of the path integral. And in that case, this is very much reminiscent to the effective action we are used to when we do, for instance, Wilsonian effective field theory in the context of particle physics. But it can lead also to a mixing between the two branches of the path integral. And that effects are the so-called non-unitary effects that physically correspond to the fact that your system can dissipate energy into its surrounding, and also that the fluctuation of the surrounding path can leave imprint on your system through the impact of noises. These effects, you cannot observe them in a theory that is invariant under time translation symmetry. And in general, this is the reason why when you do a computation in particle physics in an in-out contour, you will never observe this effect. But if you work in cosmology where energy is not conserved and your system can in general lose either energy or information, you need to tell what are these mixing between the two branches of the path integral. And so that was our first motivation. If I want to write down a generic influence functional, what are the rules that are obeyed, not only for the effective action, but also for this mixing between the two branches of the path integral? That's motivation number one. Yes, please.
Yeah. So as you're saying, this time translation symmetry is not respected. So in the normal quantum field theory, in the equilibrium, when we do, we have certain kind of symmetry in this action, right? I mean, so then in this particular case, action have a different kind of symmetry, not the exact, point of symmetry of the state.
Yes, yes, you're right. I'll come later on to explain more details how work symmetries in this context. But the general idea I wanted to share was the fact that in general, when you have dissipation, energy is not conserved. And that means that in some sense, there is a notion of time translation symmetry being broken. So that was the general idea I wanted to convey as a motivation for when you work in a context where energy is not conserved, it seems reasonable to consider these dissipative effects. But I agree with you, you can have a situation where, in fact, we'll see later on in more details how work time translation symmetry in this context.
Okay, thank you.
Do not hesitate if it's unclear later on. So the second motivation for us was the so-called effective field theory of inflation. It's an effective field theory that is extremely useful in the context of primordial cosmology because it allows us to encompass in a single formalism many different microphysical models.
Can I ask a quick question from the last slide? I mean, how do you define this boundary where you are integrating out from the environment?
Yes, that's a very important point because that's quite crucial. So for the initial boundary, we use the fact that at initial time, we specify a state for both the system and the environment. And in our case, we'll often consider a pure state, which is the Bunch-Davies vacuum. So that's for the initial boundary condition. And for the boundary condition, the upper one of the path integral, there what you use is that when you integrate out the environment, you have a constraint that the field value of the environment at the endpoint of your path integral must be the same in both the plus contour and the minus contour. And that allows you to specify what is the other boundary condition. And that comes from when you express this object explicitly, when you do the integration of the environmental sector, you will see this this constraint appearing.
I see. Okay.
Answer your question? Yes.
Yeah, thanks.
Okay, so second motivation, the FT of inflation. It's a useful formalism because it allows us to encompass in a single way most of the single field through inflationary model. That is, we have a unified framework that is very convenient to compare to the data. And the general idea of this formalism is that in order to have an inflationary period, we consider general relativity coupled to a scalar field. this scalar field is evolving in a background that is mostly homogeneous and isotropic. So we can expand it in a homogeneous background vacuum expectation value and some fluctuation. Then we decide to work in a convenient gauge, which is the one that is chosen such that all the fluctuation are carried on by the metric. That is, the scalar field is homogeneous. And since the scalar field is homogeneous, you can then use it to parameterize your time variable. That is, your scalar field will really behave as a clock. Then when you have this particular definition of time, you can define your foliation of hypersurfaces and defining normal vectors to this background value of the scalar field. So that's a convenient way to organize the geometry to describe inflation. Then the goal. Yeah, please.
Can you please elaborate why this particular gauge choice is to a polyunitary gauge?
Oh, sorry, I missed that part. Can you repeat the question?
Something. So why are you calling this choice of this time slicing as a unitary gauge? Can you please elaborate?
So that's a very good point. So that's for historical reason. But as far as I know, there is no relationship with unitary evolution. And in fact, it's important for us because the name is quite misleading, because what I will present in this talk will be an example of what we call non-unitary evolution, meaning that the evolution is not given by a Hamiltonian that is self-adjoint. And still you can define a gauge that corresponds to this so-called unitary gauge. So yes, I think it's for historical reason, but the name is misleading.
Okay, thank you.
And then the question is, what is the most generic theory I can write down that is compatible with the symmetry of my problem? The point is that the physics of inflation is very much described by having this field that corresponds to a clock. So in practice, it means that you are breaking time translation symmetry. And what the authors of this paper have realized is that the most generic parametrization of a theory you can spell in this gauge is writing down all the operators that are invariant only under 3D spatial diffeomorphism, because of the fact that you are breaking time translation symmetry. So you will write down the most generic action that will contain whatever you want that is invariant under 3D spatial diffeomorphism. It will correspond, obviously, to terms that are 4D covariant, because obviously they are a fortiori 3D covariant. But it will also contain other objects that do not transform nicely under time translation symmetry. For instance, functions that explicitly depend on time, or contraction of object with this normal vector I defined before, or other geometric object you can construct for this foliation, for instance, the extrinsic curvature. And so I can show you explicitly what it looks like. This is an expansion where the first three terms are describing the background evolution, that is the Friedman-Robertson-Walker metric that will evolve in an inflationary background, and the other terms will describe the dynamics of the fluctuation. In fact, if you want to study the theory directly at this point, it's in general quite complicated, but people have realized that it's slightly easier when we reintroduce the fluctuation of the scalar field by performing a small time diffeomorphism that we call the Stuckelberg trick. And when you perform this time diffeomorphism, what appears is that the 4D covariant term won't transform, but the function of time will be expanded, you see, in powers of this object that I will call the Goldstone boson. And other objects that do not transform nicely under time translation symmetry will also generate components that depend on this pi field. So why is it useful? Well, it's useful because in the context of inflation, you have two major simplifications. The first one is called the slow roll expansion, which is the fact that things are nearly frozen, things that are such as the Hubble parameter are nearly frozen during the inflationary dynamics. And so when you perform this approximation, you will observe that the mixing between this Goldstone boson and the fluctuation of the metric are always suppressed by a parameter that we call the first roll parameter that is small during this phase. The second useful simplification is that you can perform during inflation a derivative expansion where at late time you will pay the price of introducing derivatives. And so the towers that comes from the extrinsic curvature is much suppressed compared to the tower that comes from this object. Therefore, at the end of the journey, you have a theory that is quite simple to write down, which is the one of a shift symmetric scalar field. And you can write it down to write an EFT for inflation that is quite simple to study. In fact, when people compare this EFT to specific models, they realize that many models are encompassed within this formalism. But the point is that there are models that also escape this description and cannot be well described by this framework. For instance, if you have a model of gauge action inflation, it's a model where your inflaton is coupled to a gauge sector. The gauge sector can do particle production, and the way this particle production will then act on the dynamics of your inflaton will be through dissipative effects. So it is tempted to ask how we can extend this formalism to include dissipation and noise in order to embrace in a single framework a wider class of models. So that was our second motivation. And now I will present what we did in order to understand how to include dissipation and noise in this EFT formalism. But first, do I have any question before I move on to the construction?
Yeah, can you go back to the previous slide?
Sure.
Yeah, so one thing actually, I'm wondering that how this formalism works, first of all. I mean, the way you are saying that reintroducing the scalar field, which actually the pi, which are like applying the Goldstone. So can you please elaborate on what is the thought process behind this kind of, time?
Yes. So I can try to elaborate a bit by saying that the idea is that you are changing gauge. You were working in a gauge where all the fluctuation were captured in the fluctuation of the metric. Then you decide to change gauge by performing this small diffeomorphism. So you are in a new gauge, and you know that in general, you have 3 scalar degrees of freedom, or in general, no, you have 5 scalar degrees of freedom, 4 that are contained in the metric, and 1 that is coming from the scalar field, okay? But among these 5 scalar degrees of freedom, there is only 1 propagating degree of freedom. If you fix the gauge and fix the constraint, that will kill 4 of the scalar degrees of freedom, and there is only just 1 remaining that is propagating. And what people realize is that if you do this time diffeomorphism to reintroduce this scalar field, the scalar propagating degree of freedom is well described by this degree of freedom. So this is why this is a convenient strategy to change gauge from the unitary gauge to this other gauge.
Okay. Another point, probably you have mentioned, I have missed the point. So when you talk about the derivative expansion, so how this criteria is connected? The delta K tower is much less than the delta is not compound of the metric tower.
So the reason is that, wait, can you see here?
Yes.
The fact is that when you have an extrinsic curvature, it always appears with 2 derivatives acting on the Goldstone boson, okay? Because this term will disappear in the slow roll expansion. And it makes that the terms that are coming from the extrinsic curvature are always higher order suppressed compared to the other terms because of the fact they necessarily have 2 derivatives acting on the Goldstone boson. So that's the reason why, in general, you can drop it. But you are right that if you maybe, yeah, I think that's the main reason.
Okay,
is that your question?
Yeah.
Okay.
Can I ask a stupid question? I mean, since I have a Goldstone mode, what stops me from writing a Wess-Zumino term with RR dual or something like that?
Yes, that's a good point. That's a good point. In fact, you should write it in your theory. If I come back to the previous slide, I agree with you that at this point here, since you allow for 4D covariant terms and breaking time translation symmetry, you are allowed to write down the term you mentioned. Now the question is, why is it not appearing in general? The fact is that there is a bit of degeneracy from the operators you can write down in general here. and the one that are appearing in this expansion I wrote down here. And so sometimes some of the operators that you might naively write down are in fact combination of the other operators I wrote down here.
I see, it's redundant, you are saying.
Yes, but also let me mention that I'm not sure what I've written down here contains all the possibility you can imagine. For instance, people that study the effective field theory of dark energy, they in general include other operators. For instance, you can have the 0,0 component of the Ricci tensor that is appearing, and that will generate another type of contribution. So I don't think I've written down all operators you can imagine here.
I see. Okay, thank you.
No worries. Okay, so let's move on to the construction of an open effective field theory for inflation, where open means that the scalar field captured by this Goldstone boson pi will interact with some other degrees of freedom. And this interaction will also be through non-unitary operators, such as dissipation and noise. So the construction we developed was based, so we developed this construction in this paper, and it was strongly influenced by a past paper by Lopez-Nasir, Porto, Senatore, and Zaldariaga, where the authors studied dissipative effect in the FT of inflation. The difference with our construction is that we try to elaborate a path integral representation for this problem that is based on recent development in the field of so-called non-equilibrium effective field theory. The idea is that it works just as a usual EFT. You first identify a set of low energy degrees of freedom. Then you spell out some physical principle and some symmetries in order to write down the most generating functional that represents the theory. And at last, you want to identify a power counting scheme that allows to truncate after just a few orders and to keep only a finite number of operators. That will work exactly the same. Let me now describe this construction in the context of the open EFT. Since we want to mimic the effective field theory of inflation construction, we'll consider the same degree of freedom, that is the Nambu-Goldstone boson of spontaneous symmetry breaking of time translation during inflation. Now, the point is that we want to describe it in this so-called Schwinger-Keldysh or in contour. Therefore, we have a doubling of the degrees of freedom, one for each branch of the path integral, one for the plus contour, one for the minus contour. Or equivalently, I will often use another basis that is quite convenient, that is called the Keldysh basis, where one component is called the retarded component, which is the mean between the two branches of the path integral, where the other component is called the advanced component, and it's the difference between the two branches of the path integral. So we have our degrees of freedom. Now the question is, what is the most generic generating functional I can write down for this theory that will include both unitary effects, but also non-unitary effects that mix the two branches of the path integral? And at this point, it might seem a bit hopeless because you have a lot of options now that you allow for mixing between the two branches of the path integral. Hopefully, if you want to describe a situation that is physical, this generating functional has to fulfill a certain number of constraints. And these are called the so-called non-equilibrium constraints that were developed in a series of papers from 2015 by Crossley, Liu, and Glorioso. And this is a nice review about it.
Sorry, I have a question.
Yeah, sure.
From the last slide.
Sure.
We know that at the end of inflation at eta equals to 0 slice, we have a slightly broken conformal symmetry. So is there any limitation to break the unitarity?
So you could treat this problem in two ways. And this is, in fact, if it's fine with you, can I come back to this question in 2 slides where I will discuss the symmetry breaking pattern? Because I think it will be much clearer then.
Okay, sir.
Okay, thank you. And come to ask me again the question if it's unclear then. So I want to write down the generic generating functional. And the idea is that if we want it to encompass a physical situation, it has to respect a certain number of constraints. The idea is that, let's say that our open effective field theory comes from the fact we don't observe all the degrees of freedom, or if you want, we only observe part of the Hilbert space. It means that there exists a bigger theory that I don't know, that I will call the UV completion, that is this one unitary because it contains all the degrees of freedom I could imagine in my new universe. And if there is such a unitary UV completion, then in that theory, there exists a state that is well-defined. That is, it is trace normalized, Hermitian, and positive. And in fact, for this to exist, it pushes some constraint on your IR effective field theory you can construct. For instance, what these authors have observed is that your generic effective action that will contain both a unitary part but also this non-unitary part has to fulfill this constraint. The first one is coming from the normalization of the UV state that I don't know, which tells us that if the advanced component vanishes, then the effective action vanishes. That is quite useful because it tells you that this object has to start linear in the advanced field. The second constraint coming from the fact that there exists a state that is Hermitian makes that you have this nice constraint that tells you that if you expand in powers of the advanced field, all the odd powers have to be purely real, whereas all the even powers of the advanced field has to be purely imaginary. And at last, the fact that you have a positivity constraint imposes some constraint of the imaginary part of this object to be positive. It's a sort of positivity bound for the noise operators that will appear in this theory. So this is already a restriction to the class of OpenEFT you can write on. And I don't want to go too much into the details of where this constraint comes from, so do not hesitate to have a look to the appendix of this paper where it's detailed if you need. But the rough idea is that you can think of this object, the influence functional, as a sort of transition probability to end up in a state that is labeled by pi plus and pi minus. That is, there is an unknown environmental dynamics. I don't know what it is. It is labeled by this sigma degree of freedom. But in order for the outcome of it to be a well-defined probability, it has to fulfill a certain number of constraints. And this is why, from having well-defined probabilities, you end up having this constraint on the effective function. So that's the first restriction we will use. The second one is the implementation of symmetries in this problem. And for that, we will use the so-called in-in-coset construction that was developed in this series of papers. The idea there is that if I take a theory that is purely unitary, I have two copies of the symmetry breaking pattern, one for each branch of the path integral. And therefore, I have two Stuckelberg fields, one for each branch, that transform non-linearly under time translation symmetry. So the unitary theory has two copies of the symmetry breaking pattern. But if I implement no mixing between the two branches of the path integral, I will further break the symmetry group to an even smaller subgroup, which is the diagonal subgroup. And this is what the authors of this paper have realized. That is, whenever I accept the fact that I have non-unitary effects, that is dissipation and noise, only the retarded component will transform non-linearly under time translation symmetry, whereas the advanced component will transform just as regular matter. That is, instead of having two Goldstone bosons, one for each branch of the path integral, I only have one of them, which is the retarded component. And so now, if I want to write down my building blocks, I have two of them, the advanced field, but also the retarded field that transform non-linearly under time translation symmetry. And so the object that transforms nicely is T, the time variable, plus the Goldstone boson. So I hope it answers your question about how works the symmetry breaking pattern. The idea is that you can break time translation symmetry in a unitary theory, in which case you will have two copies of the symmetry breaking pattern in each branch. But if you induce non-unitary effects, you will further break. You have a new symmetry breaking pattern that will reduce to only one Stuckelberg trick. Is that better?
Can you explain it again?
Sorry, can you repeat?
Can you explain it again?
Yes. So what I was saying is that whenever you induce mixing between the two branches of the path integral, so let me try to explain this in a different manner. The idea is that symmetry breaking patterns do not work the same in the Schwinger-Keldysh formalism or in, for instance, the in-out path integral. And the idea is that if you were working in a unitary theory, it's like having two in-out contours, one that goes forward in time, one that goes backward in time. Therefore, it's like having two usual symmetry breaking patterns. And this is why you have two Goldstone bosons in the unitary theory. Is that part clear?
Yes.
Okay. So now if you induce some dissipation, the point is that the two branches of the path integral are now coupled together and they cannot be treated independently. So what people have realized is that instead of having two Goldstone bosons, you only have one of them that correspond to this sort of collective degree of freedom that is the mean between the two branches of the path integral. And that is the only object that will transform as a Goldstone boson. Whereas the other degree of freedom, which is the advanced field, will transform just as regular matter. So the rough idea behind it is that when you when you induce some dissipation, you are further breaking the symmetry group to a smaller subgroup. That was a bit the idea. Maybe I can come back to it later on at the end to see if I have a better explanation for it. Is that slightly better?
Yes.
Okay, thank you. So the long story short, now that we have identified the building blocks we can use for this construction, the last step we will use is to find the power counting scheme. And the one we will use is the so-called derivative expansion. That is, we will assume that our EFT is local. And we know that it is a strong assumption because when we integrate out some degrees of freedom, in general, the theory you obtain is non-local. But if you want to have a theory that is simple to write down and only keep a finite number of operators, it's important to put some restriction, and locality is a very useful one. And I would like to stress that it's an assumption that is not only used in the case of open EFT, but also in the standard effective field theory of inflation. That is, if you have a model that when you integrate out some component will lead to a very large amount of non-locality, then a priori it will be hard to embed it in a nice EFT formalism. And in that case, it will be certainly much simpler to use just direct model building. So we use this assumption, and we can come back to it later on, but keep in mind that it's a strong assumption. So if you combine all of this together, that is the non-equilibrium constraint, the in-Coset construction, and the locality assumption, you can write down this generic theory that we call the open effective field theory of inflation. We work in the decoupling limit I mentioned before, where there is no mixing between this pi field and the fluctuation of the metric, with at most one derivative per field. And what we observe is that the construction we obtain recovers in a certain limit the usual effective field theory of inflation, but also extend it. For instance, at quadratic order, the usual effective field theory of inflation has one free parameter, which is the speed of sound. And in our case, we have 5 parameters. That is the exact same speed of sound, but also a dissipation parameter labeled by gamma that controls the energy exchange between the Goldstone boson and its surrounding, and 3 noise directions that correspond to the fluctuation of the surrounding bath leaving imprint onto the Goldstone boson. Then you can go on and construct cubic operators. And what's interesting in that case is that the effective field theory of inflation is known for relating operators at different orders, so non-linearly realized boost. This is, for instance, why when you have a small speed of sound, you have a large signal in the squeeze limit, you have a large signal in the equilateral shape of non-Gaussianities. Here, the same holds true, but also for the non-unitary direction, that is, we have dissipation that appear at cubic, but that appears at quadratic, but also cubic order, and the same for the noise. So the take-home message is that with this construction, you recover the usual effective field theory of inflation, but you also extend it to account for local dissipation and noise. And now, in the last part of this talk, I will spend some time describing the kind of phenomenology you can expect from this theory. But first, do I have any more questions on the construction side? Okay, so We can also come back to it later. Now let me discuss a bit more the phenomenological aspect, and it will be more related to maybe what people are familiar to what they do when they do primordial cosmology to compare to the data. First, before we go into the details of the computation, let's start with a simple estimate in order to have an idea of what is the physics of the problem that is described by this theory. For this, I only took the quadratic action, and I kept only one of the noise direction, the simplest noise that people usually study in the literature. And I would like to point out a few differences with the usual inflationary context. In inflation, we have an adiabatic component that is a degree of freedom that freezes at late time during inflation. And this component is important because it's the one that later on seeds the fluctuation of the component we observe at late time in the universe. In our case, this is the retarded component that we play the role of this adiabatic mode. And that's useful because it means that we can relate it to observable. For instance, the observable nearly scale invariant power spectrum we have of primordial fluctuation. The point that is slightly different from conventional inflation is that the time at which this component freezes depends on the dissipation parameter gamma. That is, when the dissipation is small, that is, gamma is much smaller than the Hubble parameter h, the freezing time appears around Hubble crossing, which is as usual as the single field Searle inflation case. But now, if you are in a situation where there is large dissipation, gamma is much bigger than the Hubble parameter, and it means that the time at which this component freezes is much earlier on, controlled by the square root of gamma over h. That's the first difference. The second difference is that because of the presence of the dissipation, the physics of this problem is pretty much the one of a damped oscillator, which will lose memory of its initial condition. And what will drive the fluctuation at late time is rather the noise, that is the fact that you inject fluctuation in your system through the interaction with the surrounding bath. So you need a component that will encode the injection of noise in your system. And this is precisely the role that is played by this advanced field, which is not really a physical field, it's more an auxiliary field encoded the fluctuation of the surrounding bath. And there is an object that will encode the strength of this fluctuation, which is this beta 1 parameter that are controlling the fluctuation of the noise. So the long story short, the physics of this problem is the one of a driven dissipative harmonic oscillator. It's driven because of the background expansion of the universe, but it's also dissipative because of the presence of the gamma parameter and the noise. There are mostly two regimes of interest. One at small dissipation, where this term can be neglected compared to the other one. In that case, it's just like a usual oscillator that is also sourced by some noise. And the opposite regime can be called the overdamped regime, in which case the term that can be neglected is the first kinetic term. In that case, the dynamics is really driven by the dissipation parameter and the noise. So this is not only useful for the understanding, this heuristic estimate is also useful to understand what can we expect of interaction. In cosmology, we know that the signal we observe in the sky is nearly Gaussian with small deviation to it that are parameterized, but what we call non-Gaussianities that come from interaction in your theory. And so you can estimate the magnitude of these non-Gaussianities by comparing a cubic operator to the leading quadratic term. And the leading quadratic term in this theory is always the noise term. That's useful because, as I showed you in the previous slide, we have many different cubic operators that appear in this theory. Therefore, in this way, you can identify the ones that are the most relevant. For instance, this is a comparison between numerical integration and the heuristic estimate we can make. And this is working fairly well. For instance, you can tell that this operator that contains spatial derivative will grow linearly with the gamma parameter. This is the blue curve there. Whereas the one that has the time derivative, the comma one, will freeze at large dissipation. And this is rather the orange curve we observe. So if you need to tell a priori what are the most important cubic operators, you can use this toolbox to have a rough idea of how it will behave. Now you can rather do the explicit computation. And this is now what I would like to present. It works like just doing standard perturbation theory in a QFT in curved spacetime. That is, we first derive the propagators of theory by solving the free part of the path integral. In that case, you can analytically perform the integral. And in this so-called Schwinger-Keldysh contour, you have three propagators, two of which you are certainly very much familiar with, which are the retarded and the advanced green function that encode how information will propagate in your system. Whereas the third propagator is slightly less familiar. It's called the Keldysh green function. And its role is to tell how behave it's rather to tell the amount of fluctuation in your system. So if you want, it's a quantity that's related to the occupation of your state. And I've given here their expression explicitly in the context of an inflationary phase, where k is the wave number, eta is the conformal time, h the Hubble parameter, and gamma the dissipation parameter. These functions that appear here are Hankel functions of the first kind, which are sort of Bessel function. And here you have also some nasty hypergeometric function that will appear in the propagators. The reason why I've shown you this expression is twofold. First is to show that at the level of propagators, you can reach analytical expressions that are exact. It means that you can have exact result for the two-point function. But then you can see the complexity of the propagators, and you can imagine that when you will have to integrate them, for instance, from initial time to final time when you have some interaction, it will in general be very hard to reach analytical result because of the complicated form of the propagators. And that's something I will come back to later. So at the level of the two-point function, things are exact. Because of the symmetries we put in the problem, we are guaranteed that we'll always obtain a nearly scale-invariant power spectrum, which is this quantity I defined here that corresponds to the fluctuation of my scalar field. You can have exact expression that you can explain either at large dissipation or at small dissipation. And the take-home message is that you can fit it to the data we observe from the sky by imposing some hierarchy among the various parameters that appear in the problem. But at this point, you are not able to distinguish this theory from, for instance, standard single cultural inflation. Just a side comment, so far, I haven't made any assumption about the environment that is surrounding my system, apart from the locality assumption. But I can go one step further and ask that my environment is a thermal bath at a temperature T. And in that case, it means that there will be some relationship between the various parameters of my problems through the so-called KMS symmetry. In particular, the noise will be related to the dissipation parameter through the temperature. And in that case, when you compute the power spectrum using this formula, you will recover at large dissipation a well-known result of a class of model used in inflation that is called warm inflation, where the inflaton sector is coupled to a radiation bath. And in that case, the power spectrum scales linearly with the temperature and has the square root of the dissipation parameter. Okay. If you want, you can consider more complicated noises, but you will also obtain a scale-invariant power spectrum because of the symmetry. So that's it at the level of the power spectrum. And we are not able at the level of the two-point function to distinguish this theory from other inflationary models. This is why we turn our attention to higher order interactions that are non-Gaussianities by computing the three-point function that is called the bispectrum. Because we are working in a theory that is homogeneous and isotropic at the level of the background, the bispectrum obeys this delta conservation function of the spatial momenta. And that means that it's parameterized in terms of closed triangles in the sky. So the standard procedure is to tell what are the triangular configuration that maximize this bispectrum signal, and what is the overall amplitude of the signal. So to compute this quantity, we just developed standard perturbation theory by deriving a set of Feynman rules. We have two kinds of propagators we can use, either these plain lines that correspond to an insertion of the Keldysh green function, or plain dashed lines that correspond to the retarded green function. Whenever you have a vertex, you need to integrate from initial time to the end of inflation with some scale factor appearing in here. And so in this paper, we focus on contact bispectrum that are 3-point functions originating from a single vertex. In particular, there is no propagator in the bulk, which makes that in that case, the form of the bispectrum will always look something like this: an integral from initial time to final time with 3 propagator insertion. Eventually, we might have some operators acting on them, for instance, spatial or time derivatives, but the structure will always be the same. And now what you need to do is find a way to evaluate these integrals, either numerically or analytically. Analytically, we only find approximate solution in some asymptotic regime of interest. But maybe if you are smarter, you can find clever way to compute these integrals, for instance, using more advanced techniques such as Muller-Barnes representation. But that's for future work. At this level, let's start with this, and then we will specify 2 quantities. One is the so-called shape function. It's a function that tells us what are the triangular configuration that maximize the signal. And the other thing we will look at is the so-called FNL parameter, which is the object that allows us to tell the magnitude of the signal. Okay, so before I show you the result for inflation, let me give some insight from the flat space result, because in flat space, we can compute these things analytically, and we have a relatively correct understanding of the physics that is behind the mathematical expression. So in flat space, what you will observe is the bispectrum is always a polynomial of these kinematic variables that are the usual energy shifted by the dissipation parameter gamma, divided by a singularity structure that takes this form. This singularity structure is made of 4 different terms. The first one would be the 0 to 3 or 3 to 0 creation or annihilation of particles mediated by the surrounding mass. While the 3 other terms are the 1 to 2 or 2 to 1 scattering mediated by the presence of the environment. And so when you study this function and look at in which configuration does it peak, there are 2 regimes of interest. One at large dissipation, large gamma, where this is always this extra imaginary piece here that dominates. And in that case, the signal peak in the equilateral shape. The other regime of interest is the one at small dissipation. And in that case, it's slightly more interesting, because what can happen is that the signal becomes large when the singularity structure almost vanishes. And it almost vanishes when, for instance, this component is roughly equal to this one plus this one. That is what we call a folded singularity, which takes this form. These singularities have been studied in the past. They correspond to the kinematic exchange of 2 particles to a third one. And why we are interested in them? We are interested in them because they are quite peculiar, as they do not show up quite often in the context of cosmology. So this is a bit of a peculiar signal. Let me elaborate a bit on this folded singularity. If you want to understand the specificities of the signals, they are summarized in this slide. The idea is that the specificity of the model appears at low dissipation. In this figure, we gradually decrease the dissipation parameter from the orange to the blue curve, to the green curve. That is, the green curve is the one with the smallest dissipation. And you can see that at measure, we decrease the dissipation, we increase the signal close to this folded configuration. The second thing to see is the fact that the signal never fully diverges. And the reason why it never fully diverges is because since there is a form of dissipation, the integrals we have to compute are always convergent. That is, there is no unphysical divergence that is appearing in this class of model. And for us, this is quite important, because the only other big class of model that leads to this kind of signal in the context of cosmology are the so-called non-Bunch-Davies initial condition. But in the case of non-Bunch-Davies initial condition, the signal fully diverges when you approach the folded configuration. The third consequence is that because of the fact the signal does not vanishes close the folded triangles, it also makes that when you look at the so-called squeeze limit, which is the configuration where one of the modes is much smaller than the other two, that is roughly the case when you have a long wavelength that mediates the interaction between two other small wavelengths, then in that case, we observe that the signal vanishes. And it means that the consistency relation, which are the equivalent of soft theorems for cosmology, do apply in this class of model. So these are the three main points for this specific phenomenology. But those results were in flat space. No, we need to generalize them in the context of inflation. And in that case, the problem is that we are not able to reach so far analytical results. So we mostly relied on numerics and only some analytical results in asymptotic regime of interest. But what we observed is that roughly the main features are conserved. Here in this plot, you have two cases, the orange one at large dissipation, the green one at the blue one at small dissipation. What we observe is that at large dissipation, indeed, the signal peaks near this configuration that we call the equilateral shape. It means that it's degenerate, for instance, with a closed model of inflation where you have a small speed of sound. Whereas at small dissipation, the signal peaks in the folded configuration, here in the negative axis. And this is a specificity of the model studied that is shared also with non-Banjevich initial condition. The third point is that we still have consistency relation that holds with the vanishing of the signal close the squeeze limit. That is, it means that we don't have enhancement of the signal, for instance, when you consider scale-dependent bias in the large-scale structure. And the last important feature is that it seems the integrals are still convergent because of the presence of the dissipation parameter. For instance, if you expand the integrand at early time, you will see that will correspond to this kind of integrals to perform that are convergent whenever the dissipation parameter is non-vanishing. This point is important for us because it means there is a difference between this model to the so-called non-Banjevich initial condition. But maybe if you have a way to reach analytical results that are more robust to what we did, that would be great to confirm this observation. Okay, so before concluding, I would like to finish by a quick mention about matching with specific model, because for an effective field theory to be of interest, it has to encompass a class of models that are of physical relevance. Therefore, in our paper, we did an explicit matching with this model that was proposed by Paolo Criminelli and collaborators a year ago, which is a model where your inflaton is interacting with a massive scalar with a softly broken U1 symmetry. And the idea is that this model has a narrow instability band where you will have particle production in the subbubble regime. That means at early time during inflation. Therefore, when you look at this model from late time at the end of inflation, it really much looks like a local model with particle production, dissipation, and noise. And so the authors of the paper have shown how they can map this specific model to a so-called nonlinear Langevin equation, that is a stochastic differential equation to describe the dynamics of this Goldstone boson pi. Now, what we've shown in our paper is that this kind of nonlinear Langevin equation can be described by our EFT when we restrict to this kind of operators. For instance, the first line are the quadratic, the operators are already discussed. This one is the dissipation that is appearing, for instance, here. This term is the Gaussian noise that is appearing here. These two terms are cubic operators. They correspond in the Langevin equation to these two operators. And at last, you have two terms that are related to the noise variable. This one is a coupling of one operator of the EFT to the Gaussian noise, whereas this last term is the non-Gaussian noise. So the take-home message is that the EFT we wrote is a way to have a path integral representation for complicated Langevin equation, and so to use field theoretic techniques to solve this problem instead of using the equation of motion. That's a bit the end point of this story. So let me conclude. I told you that we wrote down an EFT for inflation that includes dissipation and noise, and we base our work on past work that was mostly summarized in this piece of work. If we assume locality, the EFT we write down is relatively easy to write, and we can study it systematically in perturbation theory. It has a few specificities at the level of the signal we expect from it, in particular, a signal in the folded configuration for the bispectrum when we work at small dissipation. And at last, you can use this formalism as a way to study dissipative and non-unitary effects in a systematic manner in cosmology or in QFT in general. Now, we have a lot of work to push this thing ahead. For instance, we need to go beyond decoupling and to understand how works the mixing between this Goldstone degree of freedom and the fluctuation of the metric. That would lead to understand the dynamics of tensor modes of gravitational waves, or to understand the dynamics of dark energy in late-time cosmology. We also have a line of work that is a connection with quantum information theory, because now that you have a system interacting with some environment, the two exchange information through entropy flows. And if you ask for these entropy currents to be positive, you can eventually place bounds on the EFT parameters that are appearing in this theory that are not the kind of positivity bonds people usually construct in particle physics, but slightly different. And these kind of bonds have been used, for instance, in the context of black holes. So we could imagine doing something similar with this kind of open EFT. At last, on the observational side, it would be interesting to carry on a data analysis in order to tell if we can place some bounds on the parameters that are appearing in the EFT using real data, such as CMD or large-scale structured data. And so my hope is that by extending the scope of effective field theory we use in quantum field theory in curved spacetime and in cosmology, we are gradually embracing some of the specificities that make that cosmology is in fact slightly different from what we are used to in particle physics. And in that way, I hope it can bring some new light to solve long-standing problems in cosmology, such as dark matter, dark energy, or the existence of a de Sitter phase in quantum gravity. So on this work, I thank you for your attention, and please do not hesitate if you have questions.
Thank you, Hama, for this wonderful talk.
Thank you, David.
Is there any question? If you have a question, please unmute yourself and you can ask the question. But I have actually some series of questions, so but before that, let me check if the others have any questions.
Sure. And also, let me just mention that if someone has questions later on, do not hesitate to send me an email, and I'm happy to chat later on. It's possible.
Yes, as this talk is being recorded, so once I upload, then possibly you can later go through, and if you have any question, please you can contact. We'll be very happy to answer all those questions. Yeah.
Sure.
So yeah, so I have a few questions for us. If you go back to the matching slide where you have talked about. Yes. So generally, when in normal effective field physics, when you integrate out, then